So welcome to our junior seminar. Today our speaker is Blaise Boissonneau from the Paris University Hausdorff, and the title is Enlarge Your Mind.
Thank you for attending. So this is joint with Anna de Maze, Franziska Janke and Pierre Touchard. And the global framework is definable valuation. So, right, if you recall, you have valuations, you have Henselian valuations. So up to that, I guess it should be fine for the audience. What's a Henselian valuation? And the goal is to say, we want to globally study the question, when is a valuation, usually a Henselian one, definable?
For Henselian valuation, you mean that the field is Henselian or quite
Henselianity? Henselianity is a property of the valuation. So it means it satisfies Hensel's lemma,
okay, yeah.
which globally means that if you have a root in the residue field, a polynomial which has a root in the residue field, then it has a root in the original field, right? So it's a property of the valuation. When is a valuation definable? And by that I mean, which means that the valuation ring is a definable set. Right? So the valuation ring, which is the set of all elements with non-negative valuation, this is a set that I want to define in the language of ring. The valuation ring is a definable set. I should write bigger. In the language of rings in my field. That's globally the question. Example, valuation is definable in the field of p-adic valuation is definable in the p-adic field. And a non-example is that if you take an algebraically closed valued field, valuation will not be definable. An algebraically closed field is strongly minimal, so it doesn't define anything which is not final. Valuation ring is neither of those things. Okay. And specifically, this little project, which turned out to be a big project, because that's Hausdorff R. It starts with a question, which we found in a paper by Kuhlmann, Krapp, and Link, which has to somehow classify the value of the definable valuation by properties of the value group. So, more specifically, the question is to characterize this class, which comes into actually two fashions. It's the class of ordered abelian group G, ordered abelian group, such that all Henselian valued fields KV have all Henselian valued field with value group, let's say isomorphic to G, have a definable valuation. This valuation definable. Okay? Let's say in all Henselian valued field KV with BK G, V is definable. And now I need to specify what do I mean by definable. Do I mean with parameters or without parameters? Well, that's two different questions. So we have here the empty set that can exist or not. So you can ask the question to characterize this set, valuations which are always zero definable, or valuations which are definable with parameters.
You can also ask externally.
You can also ask externally definable, you can also ask existentially definable, you can also ask, you can do that, you can do many things, it's just, this is somehow the sub-question. You can also remove Henselianity here, or you can restrict and say you only want to consider valid fields of equicharacteristic 0. You can do many related questions. Let's do some examples. Let's do some examples. So Z. Z is an order-dealing group. Any valuation, Henselian valuation with value group Z is definable with Robinson's formula. For that you need a parameter, but you can get rid of a parameter with a little trick by Ax, which says that actually you can quantify over the parameter. Right? You quantify over all parameter that could give you such a valuation, and then you do some tricks, and you get a definition without parameter. So Z belongs into the D empty set class. Okay, what's another nice one is Q. Well, Q, of course, is not in there. It's not in D0, and it's not even in D. So, because you look at the valued field C double brackets Q, so this is the hand field, so it's a field of formal power series from coefficients in C, an exponent in Q, and support is well ordered. This is a valued field, in fact, it's a Henselian valued field with residue field C, value group Q, and this is an algebraically closed field. So again, the valuation is not definable in an algebraically closed field. Right, so this means that in this field, the valuation is not definable. Now, of course, you will have other fields with value group Q where the valuation will be definable. But it will not be because of the value group, it will be because of other reasons. Okay? So just because there is one example, it's enough to say that's it. It's not in this class. Here's an example. So, this, which I will denote as the sum over omega star of copies of Z. This is an order-dealing group. It's sequences in Z. The ordering is, we have the smallest element here, and then, okay, this is the smallest component. There is infinitely many more. This is lexicographic sum, so you're only considering the thing with finite support, the sequences with finite support. This is an order-dealing group, and I claim that in this one, it is in D, but it is not in D0. So these classes are not equal. Of course, D0 is included in D, because if you're zero definable, then you're definable with parameters. I'm saying if you have this value group, I can define your valuation with a parameter. And that's easy, it's because this has a minimum positive element. So you just use Robinson's formula. Okay? With a parameter, witnessing the valuation with minimum positive. The element with minimum positive valuation. Okay? So, you can always define it with a parameter. But if you consider the following thing, you start by building a residue field by taking C, and now you do the same thing but somehow in reverse. This has the property, so we set K is equal to this. We have that K double bracket Z is elementary equivalent to K. Why? Well, K double bracket Z is equal to C double bracket sum of omega copy of Z double bracket Z. When you have such a hand field, this is isomorphic to, I mean, in general, K, G, H, it's isomorphic to K, H plus G. Okay, this way around. So H is the group with large elements, and G is the group with small elements.
Did you forget something behind the C?
Yes. So I'm now doing it. Okay, so you have here by definition of K, you have Z plus Z plus Z plus Z plus Z. Now I add a copy of Z on the left. That's the same thing. That's the exact same thing. This is isomorphic to K, or elementary equivalent to K. Okay, so.
Sorry, did you change order?
Yes, that's what I said here. If you have G and H, it gives you H plus G. This is how it works.
I mean, the group that you have above is on, I mean,
I'm not used yet the group I have above. I'm constructing a little field K such that if I put a Z here, it's still K. And now I will do K, double brackets this, and in here I will not be able to define the valuations.
so that you have like a copy of Z as your support, as your index.
Exactly. So, right, let me do it. So K, double brackets, sum of omega star copy of Z. I claim that this, I cannot define the valuation here. I cannot zero define the valuation here. Why? Well, because this, as an ordered abelian group, I can add a copy of Z on the right. Okay? Because this is a sequence of Z going to the left. If I add one on the right, nothing changes. So, by Ax-Kosher-Yershov, this is a field of characteristic 0. This is elementary equivalent to K sum of Z omega star plus Z, which is isomorphic to K Z sum of omega star Z. I want to keep track of the valuation here. What's the valuation? Somehow, let me just indicate it. The valuation is corresponding to this. I'm doing Ax-Kosher-Yershov, I'm changing the value group. So now the valuation that I'm defining, well, if I were to be able to define the valuation, I would define that. So now I would define this valuation in this field. But I can also play Ax-Kosher-Yershov on the residue field. If I play Ax-Kosher-Yershov on the residue field, this is elementary equivalent to K double bracket Z, double bracket sum of omega star Z. And now I change the residue field. So the valuation I'm defining is this one. And of course, these are the same field. So if I were to find the formula defining this valuation, it would define both this valuation and that valuation at the same time, which of course cannot be. Okay? So we have something in between. Now there's nothing special about Z. Okay? So if G is what we will call augmentable, that is, which means there exists H non-trivial such that G is elementary equivalent to G plus H. Right, augmentable, that's what I mean. I can add something at the end. Well then, I can play the same game. Instead of putting a sequence of Z here, I put a sequence of copies of H. And then I have exactly the same phenomenon. So then G is not in D0. Okay. If G, well, is strongly augmentable, that is the same thing, but instead of just being elementary equivalent, you want an elementary substructure. Right? Then you can play the same game, but you can also somehow play the game with fixing the parameters. And then G is not in G. So that was the first observation we had. And, right, well, note that in particular this sequence of Z here, this sum of omega star Z, is weakly augmentable, so it's augmentable by elementary equivalence. It's not augmentable by in this sense, not strongly augmentable, because it has a minimum positive element. So if you try to augment it as a substructure, you cannot add anything below the minimum positive element. So that's why somehow it's not in D0, but it's still in D.
The way you're writing it, shouldn't you say uniformly definable? So that you have one formula for one G.
Well, a priori we don't require that, but a posteriori we have that.
Couldn't you have two different formulas defining, well, sort of this one part of the valuation, I mean, and another formula defining the coarsening?
No. So,
I thought you only get a contradiction if you know that it's the same formula doing it.
it could be that there is a different formula for each field. But I'm starting with this field and I say in this field the valuation is not definable. So I fix a formula at this step. So I don't require uniformly definable for this argument. I say suppose the valuation is definable in this field. Then I get a contradiction. I mean, I fix the formula here before doing this excursion.
Yeah, but these are different fields. These are different valued fields.
Yes, but I fix the formula. I mean,
Yes, you are. I mean, but when you're fixing the formula, then you're applying the same formula.
yes, I'm already fixing the formula before doing the argument somehow. I just look at this field and I say, well, imagine that this field had
Are
a...
you saying you're fixing the field but not the valuation? So it's uniform on valuations but not uniform on fields.
You know, I mean, I'm fixing the valued field. I'm looking at the valued field K, double brackets, sum of omega star Z. And I say, in here, the valuation is not definable. Maybe not zero definable.
But then I don't understand, because the two fields that you're constructing
Yes.
are same fields but with different valuations.
I'll do it with augmentable G, and we will see. So, take G augmentable, take GH such that G is elementary equivalent to G plus H. Take K equals C, double brackets, sum of omega H. Okay? Now, K double parenthesis H is elementary equivalent to K. Okay? Good. So, suppose that there exists a formula phi in the language of rings such that it defines the valuation ring. So it defines K double square brackets G in K double parentheses G. Right? Well, now I fix my formula. Here it is. That's the formula I fix. So it could be that if I were to look at another field, the formula would be different. Okay? But here it's, I suppose it exists. Without parameters. And now, I'll say that by Ax-Kochen-Yeschoff, K double brackets G, elementary equivalent to K double brackets G plus H, because this, which is isomorphic to K double brackets H double brackets. Here, what does my formula define? Well, because this is elementary equivalent to that, Ax-Kochen-Yeschoff, I mean, this with the valuation is elementary equivalent to that with the valuation. What valuation? This valuation. So here, phi defines K double square bracket G plus H. Right? Which means it defines double square bracket, double square brackets. Okay, but now I play the same game on the residue field, and I say that Kg is elementary equivalent to K double bracket H, double bracket G. but now I change the residue field. So now the valuation that I have on this field is that one. So here, phi defines k double brackets h double square bracket. So the same formula, the same phi, we define two different valuations. Does that make you happy?
I guess I'm missing something that is probably, it's probably.
Another way to say that, which I wanted to say anyway, is to think about best definability theorem. If you've heard of this one. So, theorem of Best is saying that if you start with you have a language L and another language L prime. So here this will be the language of rings, this will be the language of valued fields. Okay? You have a theory in L prime, so in the big language. And phi the formula in L prime. Say that the following are equivalent. For all models A, B of T, such that if I forget about the big language and I only look in the small language, so if I restrict this to L and if I restrict B to L, they are equal. Well, isomorphic if you want, so equal, so they have the same set properly. Basically, I'm saying there is only one way to equip a model, a structure L, with an L prime structure so that it respects T. So I'm saying that then they are equivalent modulo L prime, elementary equivalent in L prime, and 2, sorry, because I fixed my formula phi as being in L prime. So what I want to say is that
Degree of phi.
Hmm?
Degree of phi.
Degree in phi, yes. I want to say that phi of A is equal to phi of B. That's what I want to say. Right, and then if I have this, then phi is equivalent.
Phi A is equal to phi B as
Set.
phi makes
Phi as in the set of elements of A which realizes phi.
yeah.
Yes, so I guess. A satisfy phi of A. You can only if B satisfy phi of A for all A in A, which is equal to B as a set, so that's fine. Okay? So that's what I mean. And phi is equivalent modulo T to an L formula. Okay? So, if you go back to our setting, this is the language of rings, this is the language of valued fields. This is some theory of valued field. And this will be the valuation ring, the predicate for the valuation ring, right? Or the formula saying I am in the valuation ring, whatever it's your setting. By saying that basically every time I consider a field, if there is only one valuation on this field that is elementary equivalent to my valuation somehow, then my valuation is definable. If there is a way to get two different valuations which are elementary equivalent, there is no way to Well, of course, I have to say that here I'm in L formula without parameters. Okay? Zero defined.
So if you only use the easy direction.
Well, that's the kind of the thing. Is that I claim that we use both in our paper because we actually say. So here I've been using one direction, but I'm saying if I use the other direction, this is an if and only if in Henselian valued field of equicharacteristic 0, because I need to play Expression-Herrschaft. Right? So I'll just say it. So Beth plus the trick above, the trick above, just here. You have that. If you restrict this study to equicharacteristic 0, so maybe I need to put another parenthesis. And the parenthesis is saying of characteristic 0, of equicharacteristic 0. Then I say D0 empty is exactly equal to the class of ordered abelian group G, which are not weakly augmentable, and D0 with parameters is exactly equal to the class of ordered abelian group, which are not strongly augmentable. Okay? It's just basically the idea is that, well, I did say that if you are augmentable, then there is no way to define in such a field, such my example. If I'm not definable, then I can find two different valuations on a field. And then, playing some tricks, you can assume that these valuations are comparable. And then mean that the value group of this one and the value group of that one are the same. Which means that value group is elementary equivalent to itself plus something.
Is this an elementary? It's not. Is this an elementary class?
Yes, it is because it's stable by, it is for structural reasons, stable by anything you want it to be. Stable by elementary equivalent, stable by algebra product. But it's not obvious, right? And that's the next question. Somehow first of all, we did not completely answer this question because what about fields of characteristic P, mixed characteristic or anything? Second of all, even if this was a full answer, I have no clue when is an ordered abelian group augmentable or not. On this example you can look because it's just a sequence of Z, but if I give you a random one which is very, very complicated, then it's not going to be written as a sequence of stuff. So it's unclear what it means to be augmentable.
Do you have an example for augmentable group?
Something which is not augmentable?
Yes. Example.
Yeah.
Yeah.
That is not augmentable.
Okay.
Neither weakly nor strongly.
Is it really elementary, or is it just closed under elementary equivalence?
It goes under elementary equivalence. Okay, well.
Looking at it on the definability side, if a formula works and defines the valuation range, then and let's not worry about the parameters case. Then of course it's going to work in any other model. So being
That should, yeah, right?
exactly, but somehow I'd be surprised if there's a bound on the number of formulas. That will show you that there's one formula that will either not work if no formula works, or it will work for all groups.
So you're claiming that this is not going to be uniformly definable. That's what you're claiming. Or
I guess I'm saying,
Elementary would imply.
yeah, I think exactly.
elementary would apply.
If it's
So
elementary, then there'd be one formula such that in any.
yes. So I think it is elementary, and I know that this one is elementary because I will give you actually its characterization. So that's spoiler for the end of the talk. This one we managed to characterize, and we have a first order characterization. So this one is definitely elementary. I even have the theory of them. That one, I think, for reasons, abstract reasons, it has to be elementary. But I guess we can discuss that at some point. Right, so Z is not augmentable. It's not strongly augmentable because it has a minimum positive element, so there's rigidity here. I cannot add any infinitesimal convex subgroup, right? Because I would add something between 1 and 0, which is not possible. But it could be weakly augmentable, but it's not. I guess the best way to see that is by looking at the spines, which is what I will do now. So there is a way to, I said, not every ordered abelian group is just a sequence, like the ones I was considering here, but that's actually almost the case. I mean, if you think of an ordered abelian group, either it has rank 1, so it's embedded in the reals, it has higher rank, and then you can just consider all the convex subgroups, and then it's a sequence of convex subgroups, and there you go. That's what it is. It's a bit more complicated than that, but globally that's the idea. And of course, since we're doing more theory, we're not actually looking at the Archimedean spine. We're not looking at every convex subgroup, but just at the definable ones. And that's what we call the spine. So you take an ordered abelian group, and you have two types of convex subgroup which are really important and which are definable. And you take this element in G, say not n divisible. Then I claim that this, which we call the n fundament of G, is the union of all convex subgroup of G, such that G is not n divisible modulo C. Okay? This is a subgroup, and I claim, Schmidt claims, this is definable. In fact, this is uniformly definable. That's it. I have a formula which depends on G and which outputs exactly this convex subgroup. Okay? And there is another one. An of G is the intersection of all convex subgroup of G, such that this is the convex hull of my little g, which I quotient by C. And I want that this is n regular. N regular means that if I take an interval with n elements or more, one of them has to be divisible by n. Okay? So in particular, if you are rank 1, you are n regular. But for example, z plus z will not be n regular, because if you consider the interval in 1, 0, 1, 1, up to 1, n, well, you have n plus 1 element here, but none of them is divisible by n, because this coordinate is not divisible by n. Okay? So, in some sense, it's a way to see rank 1 in first order, kind of. Because being n regular is saying for all intervals, which contain more than n elements, one of them is n divisible, this is first order. Saying I embed into the reals is not first order. Okay. Right. And this, again, is definable uniformly. And if you take these two, just consider the sequence of convex subgroup which are defined by either one of these formula, you get what we call the n-spine. So it's a way to kind of reconstruct the order type or the sequence that, you know, kind of exists already in my augmentable group more a posteriori.
So, can I ask a dumb question?
Of course.
I sort of know these conditions are the right ones to look at, but what else could one say if one hadn't already seen these kinds of conditions? I guess it makes sense to look at any kind of condition on these quotient groups that's sort of A definable or something. And you're going to get similar family subgroups.
Well, I mean, why do we only look at those, or why? I mean, these are not all the definable convex subgroup. There might be more. But there will be enough to know. I mean, we have basically, why those? Because we have quantified illumination relative to the spines. So we know that it's enough because we know that it's enough somehow. I don't have a better reason that it works.
I just sort of want to find a simplistic way of discovering this.
Well, I can tell you that Schmidt has a very nice paper where he goes through all that. So it starts with talking about the Archimedean spine, so the actual sequence of convex subgroups, and telling you why. Well, first of all, they are not first order, so of course that cannot work, and give you kind of try to. This is not the. Look at this is not the rank 1 jump below G, but it's the regular jump below G. So it's a good approximation of the rank 1. You think, well, is that all of them? And you say, no, that's not all of them, because sometimes you have more. Because of that, I can give you an example where there is one showing up, so you take our friend, a series of Z, and you join to it a series of Z over zeta. So this one is or just omega star. You know what? It's not omega star. If you want to look at every an of G, you have an element which is 0 most of the time, and then a bunch of non-zero elements, and then 0 or less. The convex hull of this element will be here, right? Will be above this coordinate. And then what's the n regular jump below it? That's the rank 1, basically. So it will be always one copy of Z. So an of G will define all the cuts here below one copy of Z. In particular, an will not see this cut. Okay, Fn will also not see this cut. But now what I do is I take the augmentable group, which is this, plus I adjoint an element which is an infinite series of 2 here, and then when we finish omega, in the omega star quadrant, an infinite series of 0. This is a new element, because it has infinite support, so it's not in the lexicographic sum. But it has well-ordered support, so I can still order this group fine. Then you consider this element, and you think, well, it's not 2 divisible, so I can compute its F2. It's not 2 divisible. It's not 2 divisible modulo this. It's not 2 divisible modulo this. It's not 2 divisible modulo this. It's not 2 divisible modulo that, because if I divide it by 2, I would have an infinite series of 1. This infinite series of 1 is not in my group. But as soon as I try to quotient by something bigger, now it's a finite sequence. So F2 will define exactly this cut. Okay? And this is new. So this is not witnessed by the A2. So somehow you might think, considering AN is almost giving you all convex subgroups, or all definable ones, but no, there is more, because of these kind of weird examples. Of course, they are very made up, but in theory they could have. So you need at least A and F, and the miracles that's it. That's all you need. Yes.
Is it true that F and G is the maximal convex subgroup such that?
Yes. Yes. So I gave you the so this is the union of all convex subgroups that G is not indivisible modulo C. It's itself a convex subgroup, and you can see that somehow, if there was a bigger one such that G was not divisible modulo it, well, it would be included in Fn. So
Are you being definable by one formula or by a set of formulas? By one formula.
The convex subgroup that I'm writing in Fn are not definable. It's just all of them. And the miracle is that Fn itself is definable, and yes, there is one formula defining Fn. So there is a formula phi of xg, which tells you x belongs in Fng. And there is a formula, and they're not too hard to do. You just have to say that
Does phi then that also depends on n?
its formula depends on n. Yes. You just say that there exists an element such that g plus n times that is almost 0, in the sense that it will be smaller than x. Or, I mean, in the convex hull of x, and now that's the thing, convex hull of x is not first order, but then we're only thinking modulo n. So I am between 0 and n times x, basically. That will be enough to say I'm in the convex hull of x, modulo n. And so that will give you this formula. And the fact that an is definable, you can cook up a formula that works, but you can also, I will tell you that an is also, you can write it as a union of Fn. So because Fn is uniformly definable, that will be fine. A lot of things to claim. This is quite very interesting. So there is also a formula psi n of xj, which tells you x is in an of g. Okay? Right. So what's the n spine? Let's go to the n spine. The n spine is the set of A and G, and of F and G. So the points in my n spine are these convex subgroups. Right? That's as a set, that's what it is. What do you have on this structure? You have the ordering by inclusion, and you have a bunch of colors. A bunch of colors is basically telling you what's the theory of the group cut that you're defining. So is it discrete, for example, or is it divisible, or many colors. I will not tell you exactly what colors are. They are predicates, which basically will tell you, you put enough predicates to determine the theory of G modulo the convex subgroup you're considering. Okay? So it's a linear order with colors. And that's the theorem of Schmidt that if you take two ordered abelian group, they are elementary equivalent if and only if their n spine are elementary equivalent for all n. Okay? So, this is where that's interesting for us, because we want to know when is G elementary equivalent to G plus something. That means that the spines of G are elementary equivalent to the spines of G plus something. Which means, morally, that the spines of G are elementary equivalent to spines of something plus the spines of G. You have to inverse the ordering because, well, because G plus H H will be a convex subgroup, which means it's going to be included in, so it's going to be in the other order of the spines. Actually, Schmidt, in his habilitation, reversed the ordering. So he says an element in the spine is smaller than another one if the corresponding convex subgroup is bigger than the other. But then in his subsequent paper, he flips the ordering again.
Just to keep on my toes, can I ask a question?
Yes.
So, I guess by abstract, basically by a compactness argument, every formula, every sentence in the language of ordered being groups is then equivalent to some other sentence in the language of
Exactly.
spine structure.
In fact, that's the other way around somehow that's proven. You prove that an abelian group has, in a sufficiently cooked up language, has quantified elimination down to the spines. So every formula in the abelian groups will be equivalent to some formula without quantifier and a formula on the end spine with quantifier potentially.
But the real question is, how effective is that function that finds the end?
I don't know, probably horrendous, probably extremely complicated. But there is an effective way to do it. I'm not sure if it's very usable somehow. And of course, it also holds for embeddings. Right. And using this, basically, in fact, using a slightly modified version of this, which is due to Kluckers and Haluk-Schock, where they also prove quantified elimination relative to spines, where they use another language for spines. We managed to do some work, and then we realized that actually most of the work we did was already done by Françoise Delon and François Lucas in 1989, in one of their papers, using this language. And we realized it's much more easy with this language. So now we are exclusively using this formalism, this language. And so...
Delon and who?
Lucas. Delon and Lucas. '89. And here were the which were very useful for us and which we also reproved independently. They prove that if G is a subgroup of H, an elementary subgroup of H for ordered abelian groups, then if you look at the convex hull of G in H, right, it's an intermediary extension. That will be interesting for us. And the reason why is, well, look at the spines of G. They must embed in the spines of H. There must be an elementary substructure. Now what is this? Well, this is all the convex subgroups which are definable in H, which are smaller than G. So it's some form. You have the spines of G, you have the spines of H, you have more convex subgroup, on the right, on the left, in between. Now I say, well, in here, what do you have? You have everything that is definable in H that is smaller than G. So everything that is definable in H which is smaller than G. So it's some form of the left closure of this in that. And if you only look at linear orders, that holds. So if you have a linear order, it's an elementary substructure of another linear order, and you look at the left closure of this one, it's an intermediary elementary substructure. Therefore, we have this. Okay? And what this gives for us, you start with any ordered being group G. You go to a saturated extension, and the saturated extension will have infinite elements because of saturation. Now you cheat a little bit, you say that this is isomorphic to G modulo the convex sum of G plus G plus the convex sum of G. Right? This is just quotienting by a convex subgroup and then adding it again. Cheat a bit by saying that it is isomorphic, you have to resaturate it over G itself. I mean, so, you know, you have to, but it works. And then what do you have? Well, G itself is also a subset of G star mod convex sum of G plus G. You know, you just include it like that. And because G is a substructure of the convex sum of G, you have this thing again. And because you have an inclusion here, an elementary inclusion here, and an elementary inclusion somehow from here to there, you know that this is actually elementary. So G is an elementary substructure of something plus G. So G is augmentable. But on the other side, that's not what I wanted. I wanted to augment it by small elements somehow, by infinitesimals. And here I augmented it by large elements. So, conclusion, all orderable groups are augmentable, even strongly augmentable, but by infinite elements. I wanted to augment them by infinitesimal. Well, you just do the same method, right? But instead of looking at this result by Delon and Lucas, you look at that result by Delon and Lucas. If you have such a pair of odd living groups, and for all elements of H, you're never defining with an Fn the subgroup 0. Yeah, it's a bit of a tricky condition, but that's where spines really play a role. And you're also never defining G0, which is the set of G infinitesimals. Let me just call it the set of G infinitesimals. So you want to never define 0 and never define the convex subgroup of infinitesimal, which are just below G.
It's not.
It's not. Thank you.
Well, this is a non-standard case.
But it's not a connected component, yes, okay. I can put the 0 here if you want, but I'm going to run out of indices if I do. Anyway. So then, G embeds into H mod G0. Okay, so here you had G embeds into the convex hull of G, and here G embeds into somehow quotienting by infinitesimals. Which here, infinitesimals don't exist, so you don't quotient by anything. That makes sense, but somehow these conditions really play a role. So not every orderable group can be augmented on the right because of this. Okay, so now we play kind of the same game, but you have to assume these conditions. Well, this one is a condition, these are a condition on H. But because G and H are elementary equivalent, and because G is an elementary substructure of H, and because this is first order in H, it's also first order in G. So saying that you can never define 0 with an Fn is a condition that you can just put on G. Okay, but this one, the sets of infinitesimal really depend on this pair somehow. So what we're saying, using this result, what we can do, you start with a group which has an infinitesimal type, so you don't want something with a minimal positive element. I mean, I guess if you have a minimal positive element, then this is true because G0 is just trivial, so you're just cosenting by nothing. And you assume that Fn of Fn is never 0. And then what you can do is you can cook an elementary extension where Fn is also never G0. So you start with G. G, an ordered abelian group, such that Fn of G is never 0. Now you say you find a G star. Actually, I'm going to call it G1. That's why I didn't want to use G0. I guess G1, which is saturated, so it has infinitesimal elements. Yes, G with an infinitesimal type, without mean pause. It has infinitesimal elements. Now, it might be that there is something here, such that Fn of that element, that new element, is exactly infinitesimals. That's bad, I don't want that. What do I do then? I resaturate. I say, well, but there is an infinitesimal type, so there must be a way to add more element in between G and G1. And I do it in a way, I choose this, that it realizes exactly the thing that will put elements in between where I want. And then I continue. And at some point, either there is nothing defining the exact infinitesimals, or I take the limit, and then in the limit, there is no way to define exactly the infinitesimals. Right, so you find your G star, that works. And then you do this, and then you do that, and now you have the G in the substructure of G star modulo G0 plus G0. And you say, well, this is basically G. Or you do the same trick as before and you say, this is actually just G. And so this one is augmentable on the right. Okay, so if there is no G such that Fn of G is 0, then I'm augmentable, strongly. Now, if there is a G such that Fn of G is 0, in some sense this is kind of having a minimum positive element. This is really something telling me 0 is really, there is a rigidity here, so I really cannot add anything. That's our result. A group is augmentable by infinitesimal, so in the correct direction, if and only if, for all G, Fn of G is not 0. And this is a first order condition. So there you go, that's axiomatization.
That's the negation.
Sure, that's one formula though, so I can negate this formula and this gives me not being... yeah. So being augmentable is a...
For all then?
Well...
Yeah. But I mean, this class is not elementary because it's the it's not a priori elementary.
Sorry,
It's
you're
a
right.
complement to it.
So you're right actually, yeah. Thank you, very good remark. So the not, well, yes, the not augmentable ones is elementary. Or is it?
The
No.
augmentable ones.
The augmentable one is elementary.
But this class over here
Is not, okay.
Is a complement.
Is a complement. You're right. So, you're right. Okay. So then that's a good question whether it's elementary or not. Okay, well, that's it, that's the end. So, one thing that I want to say before I finish, that now that we have a characterization of augmentable, we know that actually this is enough rigidity to define the valuation.
Sorry, can I ask about the statement? You say augmentable by infinitesimals. Is equivalent to just augmentable?
augmentable?
Yeah, that's what I mean, this is because when we,
The only source, the part of the theorem, the only source is infinitive.
I mean, somehow we ended up caring about both sides. Because we can also use augmentability on the other side for definability weakness that I'm not mentioning today. But yes, so augmentable by infinitesimal means G is elementary equivalent to G plus H. Augmentable by infinite means G is elementary equivalent to H plus G.
So just on the theorem, you could just create a word by infinitesimals.
I mean, depends how you define augmentable, but I guess.
Oh,
Yes.
why do you define it?
How I defined it at the beginning of this talk, you're right. You're correct. I should stay consistent at least for an hour, that's hard. So the final comment is to say that actually B is equal to the class of G which is not augmentable. Even outside of characteristic 0, because now that we have explicitly a characterization, I know that if I'm not augmentable, then there is such a G. And I can use this as a parameter, and I can use a variation on Robinson's formula to actually define the valuation, and exactly the valuations. So we don't need to restrict to equicharacteristic 0. And characterizing the weak augmentable and 0 definable stuff, for now it's still open. I think that's the end of it.